Okay, this is to provide some help with the 4.4 worksheet. I'm going to set up some of the problems for you and complete some of the problems. So question number 1 says that there are 3 forces acting on an object. So we are always going to start with the free body diagram. There's 12 newtons to the north. There's 30 to the east. And there's 14 to the west. Okay, and we are trying to find the magnitude and direction of a single force that would put this into equilibrium. So first thing we need to do is find the net force from these 3 forces. So in the x direction, we have a 30 and a 14, but they're in the opposite direction. So I'm going to subtract, and that's going to give me 16 to the east. But then I also have the 12 newtons to the north. Now I need to find the hypotenuse of that. I need to add those together. The way you add perpendicular vectors is by doing the Pythagorean theorem. So I do the Pythagorean theorem, and I get an answer of 20 newtons. But I also need to do the inverse tangent of 12 over 16, opposite over adjacent. That'll give me that this angle is 37 degrees. So right now as it is, those 3 forces would be pulling the object in this direction, but we want to make it equilibrium. So that means that our 4th force must be 20 newtons, but we want it to go in the exact opposite direction. So it would be 37 degrees below the horizontal, below the negative x-axis, and 20 newtons in size. Okay. The next one I'm going to help you out with is number 2, case C. So we have 2 different objects, so I'm going to draw 2 different free body diagrams. So for the 4 kilogram object, the force pulling down would be its weight. So this is just the weight of the 4 kilogram, because that's the only weight that's acting on the 4 kilogram. So that would be 40 newtons, because we do 4 times g, so 4 times 10. And then we need to figure out the tension pulling upwards here. And I don't know that number yet, so I'm going to just call that T1. So this is going to be rope 1, this is going to be rope 2. So that's the tension in rope 1. Now, if I take a look at that 7 kilogram object, it also has a weight of 70 newtons. I just did 7 times 10. And it also has this rope pulling down on it. And that rope pulling down is a size T1 also. So these tensions right here, I apologize I didn't draw them the same size, but those are the same size force. It's the tension throughout the rope. One's just pointed down on the 7, one's pointed up on the other one. Well, there is also the tension in rope 2 holding up this object. And our job is to find the tension in both of those ropes. So I'm going to start down here on the 4 kilogram object. That's a little bit simpler. And because I know that this is in a state of equilibrium, these 2 forces have to balance. So T1 has to be 40 newtons. Therefore, in the picture above, T1 has to be 40 newtons. Now, this is also in a state of equilibrium. So total down I have is 110 newtons. So this one, total up, or tension up, must be 110 newtons as well. Okay, going on to question number 5. We have a person pulling on a desk that is 50 kilograms in mass, and they're pulling with 200 newtons of force directed at 30-degree angle. So first thing we're going to do is draw the picture. The desk is 50 kilograms. That means its weight is 500 newtons. That goes straight down. They're pulling with 200 newtons of force, but they're pulling up at an angle, as you can see here. And this is a 30-degree angle. So immediately I need to find those components. So I'm going to do 200 at cosine 30, and this will be 173. 200 sine 30, and this will be 100. So those are the numbers that I'm actually going to be using. Those are my x and y components that I'll need to look at. I also know that there is a normal force, so there must be a normal force of the table or the ground pushing up here. I've got to figure out what that is. And I also have a frictional force opposing my motion. Now, because it's not budging, that means that this is in a state of equilibrium. So my up arrows and my down arrows have to balance, and my lefts and rights have to balance. So therefore, my up arrows are this one and this one, and they have to balance the down arrow of 500. So I already have 100 up. That means the normal force must be an additional 400 to balance out the 500. Now, so my normal force is 400 newtons. And now my frictional force in the x direction, these two forces have to balance, because those are my only x forces. So if this one's 173, friction must also be 173 in order to keep that balanced. Okay, for number 6, I'm just going to help you set up the diagram. The difference is that this time the person is pushing downward like that. So they're kind of leaning on the box leaning on the object trying to get it to move. So what the diagram would look like this time is you still have a 500 Newton force down, because that's the weight of the object. But the person pushing is pushing downward like this with 200 Newtons at a 30-degree angle here. So you're going to need to find those components again, but realize this one is pointing downward like that. There's also going to be a normal force. I will tell you the normal force is not going to be the same answer as it was last time. It's not going to be 400. And then there's also frictional force. And since this person is pushing it to the left, the frictional force that's holding it back would be to the right. Again, it is in a state of equilibrium, so apply what you know about equilibrium to solve that. The next one we're going to take a look at is question number 10. We have a box on a ramp, and we're trying to find the value of tension. So this is the only kind of scenario where I actually draw the ramp itself. So there's my ramp. I'm going to draw a dot for my box. And now the force of gravity, the weight of the object, is going to be pointed straight down. So this is my weight or force of gravity, and that is going to be equal to 200 newtons. So 20 times 10, that's going to be 200 newtons. Now, immediately, because this is a 30-degree angle here, I need to find the x and y components of the weight. I need to figure out how much of the weight is pulling the object onto the board and how much of the weight is trying to pull it downward. And whatever this angle is down here, that's the angle up here inside that triangle. So this side, which I would call FGY, because it's the, this is FGX, excuse me. This is the x part, because this is the x direction. In order to get this answer, we would do 200 times the sine of 30. Because it's opposite of the 30. So when I did that calculation, I got 100 newtons. This dotted line is going to be FGY. This is how much of the force of gravity is holding the object on the board. And you're going to do 200 cosine 30 for this one, since this side is adjacent. And that's going to give me 173. Now, the other forces acting here are the normal force, which is always perpendicular to the surface. So we want to make sure that line looks like that. It's basically an extension of this green dotted line here. That's all in line with each other. And then there's also the tension in the rope coming from this right here. So there would be tension right there. Now, again, this is in equilibrium. So the x's and y's have to balance. In this case, for my normal force, that is going to balance with the y part of gravity, because that's my y direction in this case. So my normal force is going to be 173 newtons. And my tension force here is in the x direction, and this is the other force in the x direction. So those two actually need to balance. So the tension would be 100 newtons in that case. Okay, number 11, I'm just going to help you set up the diagram. There are two different objects, so I'm going to set those diagrams up separately. First of all, for this object on the ramp, there's my object. I do not know the mass of the block, so I know it has a weight, but I don't know what it is. I do know that I also have this object over here. It has a weight of 200 newtons, 20 times 10, and there's also a tension pulling up. Now, because this object, this 20 kilogram object, is not moving, these two actually need to balance. So the tension in the rope has to be 200 newtons. Well, if I come over to my other diagram and finish it off, this one also has a tension pulling this way, and the tension throughout the entire rope is the same number. So if it's 200 over here, it's also 200 newtons over here. And now you can figure out there is a normal force. You can use the fact that this has to be in equilibrium to figure out how big this component is. And once you know the x component of gravity, then you can find the weight of the object. And once you know the weight of the object, then you can easily work back and calculate the mass. Please note the answers to these questions are on the back of the paper at the bottom. Please note the ones in parentheses are the answers if you are using 10 rather than using 9.8. So the answers that they have typed out, we're using 9.8 for G. I redid them using 10, and you'll see those answers in parentheses. Make sure you show all work, starting absolutely with a free body diagram.